Russ Jackson, thanks for joining us today. Let's dive into structs. What are they exactly?
Structs are custom data types. Think of them as containers that group together related pieces of information.
Like, say, in a financial app? Could you give an example?
Sure. Imagine tracking stock information. You'd have a stock ticker symbol, price, and volume. A struct could hold all that data neatly together.
So, how do structs differ from, say, tuples?
Tuples group data, but structs let you give meaningful names to each piece. That makes your code easier to read and understand.
So, structs are like objects in other languages, but
Exactly. They're the building blocks for defining your own data types.
and this is crucial for.
Compile time type checking. Rust's amazing compiler can catch errors early, before your program even runs.
So, what's the advantage over, say, just using variables?
With variables, you'd have separate variables for the stock ticker, price, and volume. It's messy. Structs make it more organized.
Okay, so how do you define one?
It's like creating a blueprint for your data.
Show me how.
Explaining the concept without showing code, you define the struct's name and then list the different fields, with their names and types.
So, if I want the price in dollars, I just say so?
Exactly. You specify the type associated with each field.
Can you give me an example, say, a struct representing an order?
Of course. The order struct might have fields for the customer name, order date, and a list of items, maybe another struct.
So, structs can hold other structs within them?
Yep. This is called nested structs. It's really helpful for complex data.
What if I wanted to perform calculations on an order?
You can create methods that operate on the data within the struct. This adds behavior to your struct.
Does that require any particular coding style?
Methods operate on the struct. They usually take a special first argument, the struct itself.
So, how would you calculate the total cost of the order?
You'd create a method within the order struct that takes into account the item's prices.
How about error handling if something goes wrong?
You can add error handling to these methods, returning result types to signal success or failure.
That sounds elegant. So, we can build up a really rich type system.
Exactly. Structs and enums let you define complex data types tailored to your application.
So, what are some common pitfalls or misconceptions when using structs in Rust?
One is assuming too much functionality in the struct. Keeping it focused and clean is key. Also, understand the difference between structs and enums. Each is suited to different tasks.
And what about financial applications? How are structs vital there?
Essential. For instance, modeling portfolios, tracking investments, creating financial instruments, everything is data. Structs perfectly organize this data.
Okay, rejection. This has been incredibly helpful.
Thanks for having me.
Hey Russ, this field in its shorthand looks neat. Can you break it down for us?
Sure, Matthew. It's a concise way to create struct instances, especially when parameter names match field names.
So, like in listing 5 to 5? Explain how it works.
Precisely. Instead of writing email, we just use email. It's a shortcut, auto-magically linking the parameter to the field.
Wow, that's efficient. Any downsides? Is it always better?
Well, it's more readable when names match. But if the parameter and field names differ, you need the full field underscore name, parameter underscore name syntax.
So it's a readability boost, not a performance one?
Exactly. Under the hood, it's doing the same thing, just making the code less verbose. Think of it like typing on a phone.
A shortcut for clarity. That makes sense. How about use cases beyond simple structs? Rust?
Absolutely. This shorthand shines when you're constructing complex objects where many fields get values directly from the function's inputs. Imagine building a user profile with lots of attributes.
A financial application? Like creating accounts or investment portfolios?
You bet. If you're building a stock trading app, a trade object could have a field for symbol, quantity, and price. It saves a lot of typing.
But what about error handling? If one of these values is invalid, how does it handle it?
You still need to validate the input before passing it. Shorthand doesn't replace good validation practices. Error handling would need to be done separately.
So it doesn't magically prevent bugs, just reduces some redundancy?
Precisely. It makes the code easier to understand and prevents potential typos by having an automatic mapping. Always validate input to catch errors.
Great points. Now, let's talk about situations where this shorthand might not be the best choice.
If the parameter names and field names are different, you need the field underscore name, parameter underscore name format.
Right? Or if you want to change the order, or you are dealing with a lot more complex structures.
Exactly. There are times when explicit assignments are necessary for code clarity and maintainability.
Thanks, Rust. This field init shorthand is a helpful tool in Rust, but it's not a magic bullet, right?
Correct. It's a tool in the toolbox, and like all tools, it's best used appropriately. Always prioritize clarity and maintainability.
Spot on. Understanding its limitations helps prevent potential misunderstandings.
Absolutely. It's about knowing when the shorthand works best and when a more explicit approach is needed.
Good advice. We learned how to improve readability and efficiency in a functional way, Rust.
Glad to share. Understanding these shortcuts and patterns helps you to write better, more organized code.
Russ Jackson, thanks for joining us. Let's talk about tuple structs. What are they, and why use them?
Sure thing, Matthew. Tuple structs are like tuples, but they get a special name. Think of them as labeled containers for data.
So, they're essentially named tuples?
Exactly. They hold values like tuples, but the name gives them a distinct identity.
And what's the benefit of that?
It's about type safety. A function expecting a color can't accidentally receive a point, even if they both have the same number of integer components.
Why is that important in real-world applications like financial systems?
Well, you could have transaction and portfolio value tuple structs, each carrying specific types of data. Mixing them up wouldn't make sense and would lead to errors.
So, you gain better type safety. That's a definite advantage.
Exactly. It also enhances code readability by associating a name with data structures that carry different meanings in the system.
How does that compare to just using plain structs with named fields?
Plain structs are great for describing complex data with various attributes. Tuple structs are better if you have multiple values of the same type, and naming each field isn't required.
So, when would you choose a tuple struct instead of a regular struct with fields?
When the data has a collective meaning but individual meanings don't demand distinct labels. Imagine storing RGB color values. Naming each component isn't crucial. A tuple struct would be perfect in that case.
Okay, I get it. What about destructuring them? Is that different from tuples?
No, absolutely not. They behave just like regular tuples when you try to use them.
Cool. Are there any drawbacks to using tuple structs?
Well, you lose the descriptive power of named fields. So, if your data structure becomes complex, a regular struct might be more suitable.
Right. So, you need to be careful about when to use a tuple struct versus a struct with explicit names.
Precisely. Understanding the trade-offs is key for writing robust and readable code.
Thanks, Russ Jackson. That was very helpful.
My pleasure, Matthew. We're here to help understand these crucial concepts.
Russ Jackson, welcome back to the show. Today, we're diving into structs, a fundamental building block in Rust. Let's talk about these unit-like structs. What are they, and why are they useful?
Sure, Matthew. Unit-like structs are structs with no fields. They're kind of like the empty set, but in Rust's world of data structures. Think of them as placeholders, useful when you need to implement a trait on a type, but don't want to store any actual data.
Interesting. So, they're like empty containers?
Exactly. They're not useless. For example, they can be really helpful when working with traits. Imagine a situation where you need a structure to interact with a particular kind of user interface and don't need to store any specific data. Unit-like structs become elegant solutions in such cases. It's purely about the functionality the struct provides, not the data it holds.
Okay, that makes sense. Now let's talk ownership. You mentioned this in your previous explanation. You said that the user struct in listing 5 to 1 uses the string type. Why not use the and str string slice type?
Great question. The string type in Rust owns the data it contains. That's crucial for managing memory. Using string ensures the data stays valid as long as the struct exists. With an str, a reference, we'd be relying on another part of the program to keep the data alive. That's a tricky aspect of memory management.
So, it's about control and preventing dangling pointers?
Precisely. If you use a reference, you need to guarantee the data referenced continues to exist for the lifetime of your struct. Otherwise, you get errors. Rust forces you to think about ownership to avoid these problems. If you don't, the compiler will throw errors.
Got it. Let's look at an example of what you mean. The code example you showed with the user struct and the str data type. What happens there?
Well, if you try to create a user struct with an str references without specifying lifetimes, the compiler will complain because it can't guarantee that the data referenced by the struct will remain valid. Think of a reference to something that might be deleted later, causing issues if you're trying to use that struct.
So, in essence, the string type solves the lifetime issue for us because it owns its data.
Exactly. This focus on ownership is a cornerstone of safe Rust programming. It makes your code more reliable in the long run, reducing potential memory-related bugs.
This is really insightful, Russ Jackson. It's a subtle but important point. Now, where would we see this kind of memory management consideration in a real-world scenario?
Consider a financial application, say, a trading platform. Handling user account data safely is critical. With string ownership, you don't have to worry about user data disappearing while a program uses a structure holding user details. This is how financial platforms can guarantee that they are working with valid data.
That makes a lot of sense. So, using string ensures the data is around for the life of the struct, which is important in systems dealing with important data.
Absolutely. Choosing the right data type is crucial for writing robust and reliable programs. Understanding these ownership rules in Rust is vital, especially in applications where the integrity of the data is paramount.
Thanks for shedding light on unit-like structs and data ownership, Russ Jackson. It's a crucial lesson for any Rust programmer.
My pleasure, Matthew. Let's keep the conversation going.
Russ Jackson, welcome back to the show. Today we're diving into structs in Rust. Can you give us a high-level overview?
Sure, Matthew. Structs are like containers for data. They group related pieces of information together, making our code more organized and readable.
Okay, so you're saying structs help us structure data? How does that work?
Exactly. Instead of just a bunch of variables, a struct gives us named fields. Think of a rectangle. You wouldn't just have width and height as separate variables. You'd group them together. A struct does that for us.
So, how is this different from using tuples?
Tuples use numerical indexes to access data. With a struct, we use names. It's far more readable and maintainable. Let's look at an example.
Excellent. Let's walk through the code example.
We define a struct called rectangle. It has two fields, width and height, both of type U32, and signed 32-bit integer.
So, the struct is essentially a template for a rectangle?
Yep. Then we create an instance of that struct, rect1, giving it a specific width and height. Crucially, we pass the struct by reference to the area function to avoid ownership issues, retaining ownership in the main function.
Why is borrowing important here?
Because we want to work with the data but not take control of it. If we took ownership, we might accidentally delete the data in the main function, and the function that uses it wouldn't work properly.
So, the function area calculates the area of the rectangle using the struct's width and height?
Exactly. It's clear what the function is doing. Rectangle.width rectangle height. It's more descriptive than using tuple index numbers.
So, why is using descriptive names better than using numerical indexes?
Imagine a complex data structure. Using indexes becomes very hard to read. Names make it clear what you're looking at. Financial data, inventory management, any application where data needs to be organized, structs can increase readability significantly.
That makes a lot of sense. But how do we avoid errors when working with structs?
By carefully defining the types of the fields. If you have a field for price, you'll ensure it's of the correct numerical type, preventing incorrect calculations.
What about troubleshooting if something goes wrong?
The compiler will catch many errors if you, for example, try to use a field that doesn't exist.
Okay, that's helpful. Let's talk about practical applications in finance.
In financial modeling, you could use structs to represent transactions or investments. Each transaction would have fields for date, amount, and type of transaction, which makes it extremely easy to analyze and track the financial health of an investment portfolio.
What if we have multiple types of rectangles, say, for different financial instruments?
You can define multiple structs. Each struct could be a different type of financial instrument, such as bonds, stocks, or mutual funds. They will all have different fields, but the benefit is you will be able to store them together and process them efficiently.
So, Rust structs are important for keeping data organized and readable in a variety of financial applications.
Absolutely. They improve clarity and maintainability. And, with the ability to add more sophisticated logic, you can even add features like validation checks to your data types.
Excellent. Thanks for breaking this down, Russ Jackson. We'll explore more about this topic next time. Russ Jackson, welcome back. We're diving deeper into structs today, right?
Yep, Matthew. We're tackling how to make our structs more useful, especially when we're debugging.
Okay, so we're talking about printing structs. Why is that a problem?
Well, when you try to print a struct directly, like a rectangle, Rust doesn't know how to format it. It's not clear how to present all the fields.
So, it's about formatting, not just displaying the data?
Exactly. It needs specific instructions. Think of it like asking a printer to print a document. You need to specify the layout.
So, how do we tell Rust what to do?
We use the debug trait. It's like giving the printer explicit instructions for the output format.
And how do we enable this?
Using the hashtag Derived, debug, attribute. It automatically implements the debug trait, so you can use the colon or colon hashtag. Format specifiers in println.
So, we're adding a feature, right? A debugging feature.
Exactly. It tells Rust how to represent your struct in a debug-friendly format.
What if I don't want that particular output?
You can manually implement the display trait if you want a specific output format for your users. Display is the default, but it's only useful for simple types.
But why not just always use debug? Is it better for debugging or displaying output to a user?
Debug is useful for developers, showcasing every field. Display is usually preferable for output meant for the end user. Display gives you more control.
So, what's the advantage of the hashtag Derived debug approach?
It saves you a lot of work. You don't have to write the implementation yourself.
A perfect way to get more output from your data structures. How does this connect to finances?
Imagine tracking transactions. You could have a struct for each transaction with fields like amount, date, and type. The debug trait lets you easily inspect the transactions while you debug financial models.
What if the transactions are sensitive?
Then, display is better. You might want to format the output to show only aggregated values.
So, debug for dev, display for user output. The choice matters. Why is the area function tied to rectangle structs now?
This is about code organization and clarity.
How does that work?
It's about code cohesion, keeping code related to a struct in one place, like a method.
A method neat. What about other types?
If you want to use a similar function on other types, you would implement the method on them.
Right, that makes sense. So, we have added helpful functionality with the debug trait, and now we are optimizing code organization with methods. How will we implement this?
I'll provide an example later showing how you can write an area method.
Great. So, in a nutshell, we've seen how to make our structs more debug-friendly.
And how methods can clarify the relationship between our code.
Thanks for the lesson, Russ Jackson.
My pleasure, Matthew.
Russ Jackson, welcome back. Let's talk about methods in Rust. What's the key difference between a method and a regular function?
Hey, Matthew. Good to be here. Methods are like specialized functions, but they're attached to a specific data structure, like a struct.
So, they're tied to something concrete, like a particular object in an app?
Exactly. They operate on that specific object, using a special self-parameter. Think of it as a function that has access to the object's properties.
So, what's this self-parameter all about?
Self is the first argument of any method, and it represents the instance of the struct the method is called on. It's how the method accesses and modifies the data within that struct.
So it's like a pointer to the data?
Precisely. It's essentially a way to pass the object to the method so it can work on it.
That makes sense. And how does this relate to functions?
Functions are independent. They don't belong to any particular data structure. Methods are inextricably linked.
So if I have a struct representing a bank account, a method might be to calculate the interest.
Absolutely. You can have a method to deposit money, withdraw money, or compute available balance, all actions directly related to that account.
Brilliant. So if I have multiple bank accounts, each with different balances, the deposit method would act differently on each account, wouldn't it?
Exactly, because self carries the specific account's data.
Okay, this self thing is key. How does it differ from working with a standalone function that doesn't know about a bank account?
A function has no knowledge of specific bank accounts. A method knows which bank account it's working with directly through self.
Makes sense. Any practical examples beyond banking?
Sure. Imagine a method to calculate area for a rectangle struct. Self would contain the rectangle's width and height, allowing you to calculate and return the area. A standalone function wouldn't know anything about the rectangle.
So it's about encapsulating functionality tightly with the data it operates on.
Absolutely. This encapsulation is a core principle of object-oriented programming and a key strength of Rust.
What are some potential pitfalls in using methods?
Well, you can easily confuse the data you're working with if you're not careful. If you misuse,
So proper self-usage is crucial.
indeed, a robust understanding of how methods operate within their structural context is essential to effective Rust development.
Great points, Russ Jackson. Thanks for this insight.
Thanks for having me.
Hey, Russ Jackson. Welcome back to the show. Let's talk about defining methods in Rust. You were talking about changing that area function. Can you give us the high-level idea of what we're doing?
Sure, Matthew. We're moving from a function that takes a rectangle as a parameter to a method inside the rectangle struct itself. It's like giving the rectangle object the power to calculate its own area.
So, it's like adding a skill to the rectangle object. Why is this useful?
It's all about organization. Instead of scattering area calculations all over our code, we group related operations within the rectangle type itself. This makes the code more readable and maintainable in the long run. Imagine a huge library. You don't want to search everywhere for how to calculate an area.
Okay, I see. So, you're essentially adding a new function that's inherently tied to a specific type. What's the syntax for this?
We use an impl block, implementation block. It's a keyword that tells Rust we're adding methods to a particular type. Inside the impl block, we define the area method. Crucially, the first parameter is in self.
In self? What does that mean?
That's how we tell Rust that this method operates on a rectangle object. It means we're borrowing the rectangle. We're not taking ownership of the rectangle itself. It's like borrowing a book. You can use it, but the original owner still has it.
So, we don't need to own the object to calculate its area? What if we do need to modify the rectangle?
Exactly. If we wanted to modify the rectangle, we'd use an mut self instead. If we want to move the ownership, we'd use just self as the first parameter. But borrowing and self or an mut self is much more common in practice.
How do we call this new method then?
Using method syntax. We simply call rect1.area, where rect1 is a rectangle instance. Rust handles automatically determining if we need to borrow or not.
So, there's this automatic referencing that Rust does. What is this?
It's a key part of Rust's design. When you call a method like rect1.area, Rust automatically adds in and mut, or to ensure the method signature matches. It's all seamless.
That sounds surprisingly convenient. What are the potential pitfalls to watch out for?
Well, you do have to be mindful of ownership and borrowing rules. If you try to modify the rectangle inside the area method using in self, you'll get a compile time error. And mut self is required for that.
Interesting. The compile time errors are preventing bugs before they happen.
Absolutely. And for larger projects, these methods are extremely helpful to reduce complexity and the chances of bugs.
So, the advantages of using methods in Rust outweigh the potential issues?
Definitely. It's a crucial pattern that helps in building clean, efficient, and bug-free code. You're organizing and grouping related operations into the structure, which is a common practice and is very similar to OOP-style coding.
Thanks for that overview, Russ Jackson. So, we are essentially organizing and improving the efficiency of the code in a very scalable way. A method is like a well-defined task that you can use on a particular object. Hey, Russ Jackson, welcome back to the show. Today, we're diving deeper into Rust methods, specifically those with multiple parameters. Can you break down this concept for our listeners?
Sure thing, Matthew. Methods with more parameters are just like functions, but they're attached to a specific data structure, like our rectangle struct. Instead of a standalone function, we have a method within the rectangle struct, which can operate on data inside the struct.
So, this can_hold method you mentioned, what's it doing exactly?
It takes another rectangle as input, and it checks if that rectangle can fit entirely inside the first one. Think of it like a container, right?
So, you're checking if it can fit within the dimensions?
Precisely. It compares the width and height of the two rectangles. If the width of the second rectangle is smaller than the first, and the height of the second is smaller than the first, it returns true. Otherwise, false.
How does this relate to financial applications, say, stock portfolio management?
That's an interesting thought. You could imagine representing stocks as rectangles, with the width representing market cap and height representing price. The can_hold method could determine if one portfolio can fully encompass another.
But the actual values here aren't directly related to financial value, right?
Correct. The method operates on the relative size of the rectangles. The values themselves are not used. This is just an analogy to show how methods like this work with multiple parameters.
Okay, so you're saying these parameters are essential for the method's logic?
Absolutely. The parameters, in this case, the other rectangle, are crucial to the logic within the can_hold method. Without them, you can't tell if one rectangle fits in another.
What happens if we try to use the method with different types? Or if the second rectangle is bigger?
The compiler will complain about type mismatch. The can_hold method expects another rectangle as a parameter. If you pass something else, like an I32, there's an error. If the other rectangle is larger than the first, the method will correctly return false, as it wouldn't fit.
So, the method's logic is directly dependent on those parameters?
Yes, entirely. That's the whole point of passing parameters. They add flexibility and enable a method to operate on specific data you provide.
Interesting. Are there any potential pitfalls or common misconceptions about using methods with multiple parameters?
One common mistake is forgetting the AND when passing a reference. If we didn't use and rect2 in the example, the program would likely fail because ownership of rect2 would be transferred.
So, passing by reference is crucial for this example?
Very much so. It's critical. You're only borrowing the data, not copying it.
Thanks, Russ Jackson. That was a great explanation. This has definitely improved our understanding of methods with more parameters. Russ Jackson, thanks for joining us. We were just talking about structs, which are great for organizing data. But enums? What's the deal with those?
Enums are like a powerful toolbox. Structs hold different types of data in a fixed format. Enums let you define a set of distinct possibilities for a single value.
Okay, so possibilities? Can you give me an example?
Sure. Imagine you're building a financial app. You need to represent different kinds of transactions. You could have a deposit, a withdrawal, or a transfer. A struct wouldn't do a great job here because you're defining types. This is where enums excel.
So, instead of a struct that contains all the transaction details, we're focusing on what type it is?
Exactly. An enum lets you specify, this value is a deposit, this value is a withdrawal, and so on. It's a cleaner way to define these possibilities.
How does it help with readability compared to using a bunch of if/else statements?
You don't need so many if/else statements to check the type of the transaction. Enums, make the code much more maintainable and easier to understand.
So, how would this work? Give me a more practical example.
Let's say a transfer transaction requires a destination account. You can make an enum case for a transfer which holds that extra data.
That's cool. Are enums only for things like transactions?
No, absolutely not. They can be used for practically any kind of choice. Think about different types of assets in a portfolio. You could have a stock, a bond, or real estate. Defining these as separate cases in an enum makes your code far more readable and manageable.
So, it's not just for finance, then.
Right. They work great in any domain where you have a set of possible values. Imagine an enum to represent different status values of tasks in a project management system.
But could there be downsides? I mean, is there an important constraint or limitation when using enums?
You can't easily mix data types. An enum represents a single value at a time, not all possibilities at once. You can have data in the enum cases, but only one case is valid at any given time.
That's important to keep in mind. So, enums are great for representing different categories, but not for a single object with multiple types of data.
Precisely. Structs excel at that. Using the right tool for the job makes your code much stronger.
Good point. Enums seem powerful for defining these distinct types of data.
Indeed. They are super useful for working with different types of financial transactions or different assets in a financial portfolio. And they help keep your code readable and structured.
Thanks for the clear explanation, Russ Jackson. That was incredibly insightful.
You're welcome, Matthew. It's always a pleasure.